Hi, everybody. Today we're talking about resonance, and we're going to talk about resonance in series and parallel RLC circuits. So let's write down what we know. We know in this circuit here, I meant to write that. We know in this circuit, we know that XC is equal to 1 over 2 pi FC. Okay? And we know that XL is equal to 2 pi FL. And we know that ZT is equal to ZR plus ZL plus ZC. So the total impedance is equal to the impedance of the resistor plus the impedance of the inductor plus the impedance of the capacitor. We also know, if we're going to do it another way, that it is the square root of R squared plus XL minus XC squared. Okay, so that'll give us our total impedance in this circuit. So there comes a time we know that XC is inversely proportional to frequency. And we know that XL is directly proportional to frequency. Okay? So what happens is if we made this X, okay? We made this negative X and positive X. So that'll be above 90 degrees, less than 90 degrees. And this is frequency. Okay? We know at very low frequencies, we know that XC is high, okay? And XL is just about 0. Okay? Then as frequency increases, we know that XC keeps decreasing as frequency increases. And we know that XL keeps increasing, all right? They don't necessarily go in parallel lines like that. But at some point, so here is XC between here, okay? And here is XL, okay? And it keeps increasing. But there does come a point where we're here, okay? There comes a point here, XL, where XL and XC are going to equal each other. All right? And that point is called the resonant frequency. So resonant frequency, okay? And it's also given as that, okay? And that point there is where XL is equal to XC. Okay? And that's a very big point there, the resonant frequency. Because what happens there is, so at the resonant frequency, XL is equal to XC. Okay? The inductive reactance is equal to the capacitive reactance, which means that ZL and ZC are now 180 degrees out of phase at the same magnitude. Okay? So what happens now is we now have ZT is equal to Z of R, right, at angle 0, plus it's equal to XL at angle 90 and XC at angle negative 90. Okay, so if these are both the same, if XL and XC are the same, that means these will cancel each other out, which tells us that ZT is equal to ZR. All right, ZT is equal to ZR. Now, because at FR, right, since XL is equal to XC, right, that now means that VL and VC cancel each other out. It doesn't mean they're 0. Okay, we're going to prove that in a second. They cancel each other out. So that means that VR is now equal to E. And that means that IT is equal to VR over R, or E over R. All right? So that's what that means. Now, what happens is, if we, so at resonant frequency, okay, at resonant frequency, that means that our impedance is at its lowest. So at FR, okay, impedance is its lowest value. It also means IT is at its highest value, okay? And since Kirchhoff's law says that it's the sum of all the voltages in this loop equals 0, the algebraic sum, all right? That also means that VR is at its highest. Okay, so those are very big points to understand, all right? But it does not mean that VR and VC are equal to 0 or that XL and XC are equal to 0. But how do we know which frequency this happens at? How do we know what frequency XL would be equal to XC? Okay? And the way we calculate that is resonant frequency is equal to 1 over 2 pi square root of LC. Okay? So that is the formula right there, 1 over 2 pi LC. So in this case here, it is 1 over, and 2 pi LC is 2 pi times the square root of 100 millihenries times 1 micro. That's what we have there. So what we end up with there is, if I was to do it in my calculator, I would say that it is, regular mode, is 1 divided by 2 times pi times, I'm going to put square root of, and in brackets, I'm going to put L, so it's 0.1, 100 milli, times 1 micro. Okay, and we get 503.3 hertz. So at 503.3 hertz, this circuit will be in resonance. So what does that mean? Well, at 503 hertz, XL is going to be equal to 2 pi FL, which is equal to 2 times pi times F, which is 503.3 times 0.1 for 100 millihenries. Then we get 316.233 ohms. So 316.233 ohms. Okay? And then XC is 1 over 2 pi FC, which is, if we work that on here, 1 divided by 2 divided by pi divided by 503.3 divided by 1 micro. So we get the same 316.223. 316.223. So we're off by 0.01 because of rounding, okay? So that's what we have there. So now, what happens? Well, if we were to figure out ZT, ZT would be ZR plus ZL plus ZC, and that will work out to, if you figure it all out, it will work out to 200 ohms. That will work out to 200 ohms, which is R, okay? Because these cancel each other out. All right, so that means IT, that means that IT is equal to E over ZT, which is 100 divided by 200, which is 500 milliamps. All right, so that is the highest point that it's at. Now, what happens is VR is going to be equal to E, which is 100 volts. Okay? So if we were to graph impedance, okay? So if we were to graph Z, we would get, so this is frequency, we would get Z would be at its minimum value. Z would be at its minimum value at the resonant frequency, okay? So this is Z, okay? So if Z is at its minimum value, that means that IT will be at its maximum value, and so would VR. Okay? Now, what happens is as you approach resonant frequency, okay, Z is dropping, VR is going up, and IT is going up. And then after you pass resonant frequency, you'll notice that Z is going back up again, and VR and IT are going down. All right, so we're going to have a short little demo on that. Okay. So here in Multisim, I have that circuit set up. Okay, so what I do is I set the function generator to have 3 volts RMS. Okay, so we calculated our resonant frequency to be 503 hertz. All right, so let's look at what happens here. We're at 400 hertz right now, and look where our voltages are. So the VC and VL are not the same, and VR is where it's at, 2.4. So let's move closer to our resonant frequency. So we're at 400. Let's go to 450. Okay, let's see what happens. So we're at 449, 450, whatever. So we're here. Now, you could see that VL and VC are coming closer together, and you can see that VR is approaching 3 volts, which is our RMS supply voltage. So let's go to 480. Let's go to 480. Okay, and even closer yet, let's go to 500 and get closer to our resonant voltage, our resonant frequency, which is 503. So there we are. All right, so we could see that VR is almost at 3, and we can see these are coming very close together. And look what happened to IT. IT is now at its max. So let's move away from resonant frequency now. Let's go from 500 to 550. Okay, 500 to 550. IT went down, VR went down, and now VC and VL are moving apart again. But look how they come. VC is lower than VL, above resonant frequency. Let's go below resonant frequency again. Let's go below resonant frequency, okay? And they will flop. And they will flip, okay? Let's go to 450, and they flip. So VC is higher than VL. Then let's go above resonant frequency. And now VL is higher than VC, okay? So, but when they hit resonant frequency, they are the same. All right? So at resonant frequency, the capacitor and the inductor cancel each other out. And that is a very big concept for us to learn. All right? So now, if we go back to our handy sheet. So now, if we're doing a parallel circuit, if we're doing a parallel circuit, okay, then we know in this circuit, we know that IT is equal to IR plus IC plus IL. Okay, we know that to be true in complex numbers. All right. Now, we know that IC is equal to E over ZC. And we know that IL is equal to E over ZL. Okay, so we know those facts. Now, here, also, we know that IR is equal to E over R. Okay, and that will not change with frequency. As the frequency changes, XC and XL change. Okay, as frequency changes, XC and XL change, which means ZC and ZL will change, which means that IC and IL will change. But IR does not change because the resistor is not affected by frequency. So at resonance in a parallel circuit, at FR, okay, we know that XL is equal to XC, right? We know that. So that also means that ZL, therefore, ZL is equal to ZC. We know that, which tells us now that IL and IC will cancel each other out because they're 180 degrees out of phase and the same magnitude. Okay, they're 180 degrees out of phase and they're the same magnitude. So what does that mean? If IL and IC cancel each other out, that means that IT is equal to IR. Okay. Now, at resonant frequency, since we've lost those branch currents, that means that IT is at its lowest point. If IT is at its lowest point, that means that Z must be at its highest point. Okay? All right? So IT is at its lowest point and ZT is at its highest point. That does not mean that IC and IL are equal to 0. It just means that IC and IL cancel each other out. All right? So if we were to take this circuit here, our resonant frequency for this circuit is 1 over 2 pi square root of L times C, okay? Which is 1 over 2 pi square root of C, or L, which is 90 millihenries, times C, which is 1 micro. Okay, bring that over. So if we were to calculate that, we would say that it would be 1 divided by a bracket 2 times pi times the square root of bracket 90 milli times 1 micro. So we have 530.516 hertz. So 530.52 hertz. 530.52 hertz. So it's at that point where XL equals XC. So what is it? XL is equal to 2 pi FL, which is equal to 2 times pi times 530.52 times 90 milli. And we get 300 ohms. And then XC is equal to 1 over 2 pi FC, right? Which is 1 divided by 2 divided by pi divided by 530.52 divided by 1 micro. Okay, we have that. And we get 299.998. Okay. So that means that ZL is equal to 300 angle 90, and ZC is equal to 299.998 ohms angle negative 90. All right. So if we were to calculate ZT and ZL and ZR, okay, or sorry, IL, IC, and IR. So IL is E over ZL, which is equal to 100 over 300 angle negative 90, which is 100 divided by 300. So we get 333.333 milliamps, an angle of 90, and IC is E over ZC, which would be 100 divided by 299.998. Okay, so same thing, 333.333 milliamps, angle 90. All right, and then IR is equal to E over R, which is 500 milliamps. So if we were to add these, if we were to add them, IT equal to IR plus IL plus IC, we would find that we have 500 milliamps, angle 0, plus 333.333 milliamps, angle sorry, this should be a negative 90. That should be a positive 90 at angle negative 90 plus 333.333 milliamps, angle 90. These cross each other out, right? Those cross each other out. So we end up with IT is equal to 500 milliamps, which means it's equal to IR, right? So what can happen here is if we need to detect if a signal is at the resonant frequency of the circuit, if it's a parallel circuit, we can just have a way of comparing IT and IR. And when IT and IR equal each other, we know the circuit's at resonance. In this case, if we compare E and VR, when E and VR are the same voltage, then we're at resonance. That's how we know. All right. So where can we use such a thing? You see here that these impedances cancel each other out, basically, right? They cancel each other out. So what we have, so we see here also at resonant frequency, at FR, ZT is equal to R. ZT is equal to R, okay? And here, also at resonant frequency, ZT is equal to ZR, right? So where is something like this used? Well, there are different ways, and you're going to learn more about resonance and tank circuits and stuff when you get deeper into the program. But if we want a couple of quick examples, all right? This here, we can have, just if we just want to take a simple amplifier, okay? Want to take a simple amplifier, and we have our output. We'll have our input here, and we'll just come in with an input capacitor. All right. And then what we'll have here is our output. Okay. We should probably put a capacitor in there. So we have our output. Then what we'll have up here is a tank circuit, okay? We'll have a tank circuit up here. And this tank circuit will be tuned. So what happens is L and C, Q, C1, C2, we'll call this C3. So what will happen here is we could tune this circuit that it will amplify most of the signal when the input signal is at the frequency that is determined by the frequency here will be determined by 1 over 2 pi square root of LC. All right. So if this has been set up that the resonant frequency here is 1 kilohertz, then we'll say that when the signal coming in is at 1 kilohertz, it will amplify most of that signal. If the signal is 300 hertz or 1200 hertz, you will not get as much of an output. But when you hit the resonant frequency, then these two will cancel each other out, which means there'll be no voltage drop across here, which means you have maximum voltage at the collector. If these are not in resonance, that means that there is an impedance here, meaning that there will be a voltage drop, so you'll have less for your output signal. Okay, that is one example of where you might see such a thing. Okay, so this is called a tank circuit. They don't always look as nice as this, but it's just an introduction to where you might see these. Okay, another place where you might see these, or not might, where you will see these, is if we share that. So what we have here are basic AM radio tuners. So what happens is you have, over here on the left, you have a variable capacitor in parallel with an inductor. Okay, so the radio station that this tunes into is determined by the formula 1 over 2 pi square root L times C. And if you keep changing C, it keeps changing the resonant frequency, which changes what this tuner will be tuning into. So all of your carriers for your different stations are at different frequencies, okay? And this will determine what frequency it will be picking up at. And then another example is we have another tank circuit over here. An inductor and a capacitor in parallel with a variable capacitor. You could also have a fixed capacitor and a variable inductor, but whatever changes the outcome of 1 over 2 pi square root of LC. Okay, so that is an introduction to resonant circuits. So remember, we have them in parallel, we have them in series. We'll be doing more of those as we go through the program. Thanks for watching.